Hello everyone, welcome to the video number 11 of this video series on understanding FEA concepts with 1D example. So in last video we have seen different element types. Here in this particular video I will just show you stiffness matrix for few element types. Okay, so previously we have derived actually the stiffness matrix and FEA characteristic equation for 1D bar element, but here we are not going to derive for all the elements. We are just going to show you last FEA characteristic equations, okay, the final derived one. Okay, so this is the no first okay, first order bar element, okay, which is also called linear bar element. We have seen it is also called first order. Okay, so this is a element stiffness matrix. As we know, this is a displacement vector for element and this is a force vector element level. Okay, so this is element characteristic equation. This we have already seen. Characteristic equation. Okay, so similarly for second order bar element means quadratic bar element is also called truss element. Okay, which will have mid side additional mid side node, so three noded element. And if you remember in last video we have, whenever I tried to explain different element types, I have also shown you the degree of freedom per element. Okay, so reason for that is that, so the k element, so k element matrix stiffness matrix size is always uh, is degree of freedom per element by degree of freedom per element. Okay, so it is nothing but size is nothing but degree of freedom per element. Okay, square matrix. So if you remember in second order, for second order bar element we said the degree of freedom in 1D space, okay, is per element is 3. Okay, 1 degree of freedom for each node. So K matrix is 3 by 3 simply. U matrix is 3 by 1 and F matrix force vector is 3 by 1. Okay, and for first order bar element which is linear beam first order beam element, which has translation plus rotational degree of freedom. Okay, and for this first order beam element, degree of freedom per element is 4. So stiffness matrix is 4 by 4. This is 4 by 1 and 4 by 1. Okay, okay, so this is a stiffness matrix and this is a displacement vector where u1 is displacement at node 1, rotation at node 1, displacement at node 2, rotation at node 2, theta 2, and force vector is F1 is equal to force at node 1, M1 is moment at node 1, force at node 2, and M2 is moment at node 2. Okay, similarly this first order beam element, uh, for if it is in, if it is represented in 3D space, okay, XYZ space, this is only in X space, okay, 1D space. Okay, yeah, so we already written here, so 1D space. For 3D space, okay, so this is a stiffness matrix. As we know, 1D beam element, okay, uh, 3 translation plus 3 rotation for node 1, and similarly for node 2, 3 translation plus 3 rotation. So degree of freedom per element is 12. So therefore stiffness matrix is 12 by 12, 12 by 1, this is 12 by 1. Okay, so these are translation at in three different three different axis. Okay, translation in three different axes. This is a rotation about three axes for node 1. This is translation about three axes for node 2. This is rotation about three axes at node 2. Okay. Similarly, these are force moments at node 1 and these are force moment at node 2. Okay, so why I have I'm showing you this, you don't actually need to remember all this stiffness matrix. Okay, okay, just understand the dimensionality of element, okay, degree of freedom for element, okay, and what is the size of stiffness matrix and those things. So that is sufficient. Okay? We don't need to remember all these things. So only what I wanted to show you here, the key takeaway. If you see, observe the K matrix, okay, element stiffness matrix, okay, it consists of two things. Okay, one is geometric parameters and material parameters. Okay, if you take a 1D bar element, okay, this one AE by L, AE by L. So geometric parameters are A and L. Similarly, material parameter E. So we can say uh, the stiffness matrix for element is nothing but it is a geometric stiffness plus material stiffness. Okay, so if you want to understand, no, try to physically understand this. Okay, uh, if I say like no, there is a particular structure, for example, something like this. Okay, and let's take this is a steel. Okay, and let's take another material, another structure of plastic. Okay, let's say take something like this, or let's take not plastic, uh, aluminium. Okay, okay, so for steel, okay, material stiffness E is very high, right? I mean, it is not very high, but it is high compared to aluminium. Okay, aluminium Young's elastic modulus is 70,000 megapascal. Okay, so steel is more stiffer than aluminium. Okay, so if I take this structure, okay, uh, we cannot say that this structure, if it is made of steel, it is stiffer than this aluminium structure. Okay, we cannot say, because this structure, the geometric stiffness, okay, may be less than geometric stiffness of this structure. Okay, okay, if I just take no axial stiffness of this structure, okay, we can imagine that this particular structure has a higher no geometric stiffness. So that means the structure total stiffness of the structure is combination of geometric and material stiffness. Okay, so from that we have to decide which is more stiffer. Okay, geometric plus material. Okay, other example, no, if we take some, let's take a no, plastic, okay, or let's take aluminium, okay, aluminium, okay, and if we take a aluminium needle, okay, we can easily pierce or make a dent into steel structure, okay, with aluminium needle. So we can say like in this case this is also stiffer. So it is basically what I am going to, I'm just trying to give some examples, okay, you can imagine many other examples. What I'm saying, total stiffness of the structure is geometric stiffness and material stiffness, okay.